I did. I don't know if you saw it, but I did actually put the PowerPoint in PDF format on Canvas. So you can, if you want, you can look at the slides later. And we're going to record this, as you noticed. So I will also make it available if you want to look at the recording. So I will start sharing my screen. So can everybody see the slides? So we are going to talk about the paper from Chandran et al. About time frequency analysis. And they actually do a good job, I think, in comparing a number of methods. So feel free to interrupt me. We also have time at the end when we stop the recording to talk, etc. But if you need answer to a question immediately, just interrupt. So yeah, the thing is that that you look at neuroscience data, it is usually, as it is highlighted here, non-stationary. And that's not always easy to deal with, because as we know that most signal analysis procedures are based on the fact that the data is stationary. In order to deal with it, you can kind of use a short time of analysis, the short time Fourier transform, or taper method that in itself is not short-term, but a short-term version thereof. The wavelet transform, that's actually by definition adaptive in that sense. The Hilbert transform is a little bit of an outlier, but can give you an idea of instantaneous amplitude and phase, albeit only from a narrowband signal. So in that sense, it also has its limitations. And this in this paper is trying to make an advertisement for the matching pursuit approach to deal with this problem. And to some extent, it actually works. So, sorry. So basically, the introduction is again pointing out that you have to look at short segments to avoid that you get from one end to another end, and then due to non-stationarities, you're comparing apples and oranges. The problem if you take short segments is that you cannot kind of determine time and frequency components with arbitrary precision. They're basically related to each other. We'll talk about that a little bit. What they do is they, and that's kind of highlighted here, they have LFP recordings from the visual cortex. They do a more or less an evoked potential. They stimulate every 600 milliseconds and then present something as a stimulus for 400 milliseconds. And they sample at 2 kilohertz, 2000 samples per channel per second. And they use then this individual recordings and the average to look at the distribution in time and in frequency. And the first one that they look at, of course, is not surprising, is the Fourier transform. And that's an equation we know. Although in this case, I want to point out they have a normalizing factor of 1 over the square root of 2 pi, which we did not use. Some papers do that. A problem if you do that is that you also will have to rescale in order to make Parsifal working. And Parsifal is the theorem that says that the power in the time domain equals the power in the frequency domain. Of course, if you start to rescale the Fourier transform, you have to make sure that you adjust that scaling at the other end as well. In the paper, they point out, they kind of give you equations in continuous time, but of course every analysis that they do is in discrete time. That's the same thing we actually have been doing frequently, so that's nothing new for us. An interesting thing that will come back, and so I'll point it out here, is that they nicely define the inner product. That's also known as the dot product, and that's also known as the scalar product. So don't be confused with that. It's all the same thing. And it's basically defined by this integral. And sometimes this integral is also replaced by these triangular brackets. We will see that later. Here, by the way, the star is the complex conjugate. Parseval's theorem we just discussed. And basically, in this case, we kind of know that the phase and the frequency is of course integrated over this 200 milliseconds period. Now here is the equation that is being used for the short-term Fourier transform that looks very similar to the Fourier transform. Smartly enough, they now basically omit this term, so they won't have issues with Parseval. And the only difference between the Fourier transform and this one is that there is a window that is represented by ht minus tau. So h is not the unit impulse response here, it's the window or the taper. That's basically the same thing. And that window and that taper is shifting over the data. And then the data shifted with that window is being transformed. So now you get a transform that's basically a function of frequency, which is always the case, but it's also a function of the position over the whole time series, the tau of this case. Note that we, in this case, strictly speaking, that we are determining the Fourier transform of a product, namely the product between ft, the signal, and its window, the ht minus tau. So the first figure is kind of doing this analysis, this short-term analysis of the Fourier transform. As a matter of fact, there's already figure 2. I want to kind of somehow skip this figure. So I wanted to kind of show first the first figure, which is just the standard Fourier transform. And what they do is they determine the amplitude spectrum, the phase spectrum, and the power spectrum, albeit that the power spectrum is shown on a logarithmic scale. And what they do is that this is their average signal. Here is the stimulus. This is pre-stimulus. This is in part, of course, and they are looking at this area of the response. And just as we did initially when we looked at fitting sine waves to, let's say, a square wave, they're fitting a couple of sine waves just as an example to this signal. And here you see how it fits, and you see that the most important one is the red one, which is actually around 50 hertz. 45 hertz in this case. In the amplitude spectrum, you can actually see these. This is the black one, this is the red one, and this is the green one. And in phase, you can see that too, but of course, the phase is not that informative in this particular case. And the same peaks you can also see in the power spectrum, albeit a little more difficult because they're using a logarithmic scale. I do want to point out that I immediately noticed, and later they come back to that, and I will come back to that too, is that there is a 60 cycle peak and a 120 cycle peak, which means that they have some issues with hum and the harmonic of hum. But I come back to that. So then the next thing is that instead of doing the whole Fourier transform, they now do this stepwise short-term Fourier transform. And here you have that window that we were talking about. This is ht minus tau that is being shifted over your data. The blue one is the data, and these are the windows that are being shifted. They give you some basis functions that fit into that window. Just again, a couple of examples. There is a green one, there is a red one, and there is a black one again. And you have to realize that now per window, you are going to get a power spectrum. So you get a power spectrum here, a power spectrum there, a power spectrum there, etc., etc., etc. And that power spectrum you can now basically represent by this tile diagram. And the reason is as follows, that if you do have a frequency resolution of, of 0.1 second, which is in this case the step of your window, see, minus 0.05 to 0.05, so the total is 0.1. That means that the resolution window is 10 hertz. So that means that the frequency resolution in the tile is 0.1 second in the time direction and 10 hertz in the frequency direction. And these tiles are basically shown here. And so you have the tiles per short-term Fourier transform. And for instance, this black one would basically fit this tile. The green and the red one would fit in that tile. The red color in this case just indicates the waveform, not the intensity. What they do is they now actually look at the spectrum and they present the color spectrum now. So now the tiles are being filled in with a color-coded spectrum. So instead of drawing the spectrum here, they basically assign a color to each of the intensities, and they then make this color diagram. By the way, of course, they are not showing you the whole spectrum, because the spectrum in this case, because they sample with 2000 hertz, would move up to 1000 hertz, and that of course they are not going to display, because for the LFP that is not the most relevant part of the spectrum. So if you want to kind of get some further idea how this is done and how it is done in MATLAB, I refer to these pages in the textbook. There it is basically done, also in conjunction with an application of wavelets. We may actually talk about that next week on Wednesday if we get to it. So in that sense, you can say that what we did with this short-term Fourier transform, we kind of looked at somewhat kind of like a filter bank representation, because here you have again the equation of the inner product. And for that reason, this one is now the complex conjugate, because that's how the inner product was defined. And so this is just the same equation as 2. It's just rewritten as the inner product. What happens here is that this is kind of, we can kind of consider this, the window is being multiplied in the time domain with the signal. And if you multiply in the time domain, then you get a convolution in the frequency domain. So it's just the opposite as what we have been doing with filters, where we have convolution in the time domain and a multiplication in the frequency domain. Here is just the other way around. We multiply the time domain with the window. And then what we then do is we basically then get the convolution of that window with a particular frequency of a sinusoidal wave. So I can maybe better explain it here, and this is again something that is outlined also in the textbook. So if you want to read it over, you can do that. But here you see 3 pictures of what a rectangular window Fourier transform would be. And so if you have a rectangular window and you kind of shift that over your signal, you would get for each frequency, you would get a convolution of this window with that particular frequency. And so as you can see, each window, and it depends a little bit on how broad your window is, but and the size of the window. But depending on that, you can see that every window can represent a bandwidth, because this is the frequency and this is the intensity. And so since we have a number of these sinusoidal signals, waves, we have basically for each frequency, we have such a bandwidth. And for that reason, you could say, well, that the time frequency analysis, short-term time frequency analysis, is basically can be considered a bunch of band filters. So now let's get back to the problem that we were talking about, is that, well, when we look at the data, we have non-stationarities in the data. I'm going to talk about that a little bit more in the next slide, but it is basically what is called the time frequency uncertainty principle. And it kind of relates also to the Heisenberg uncertainty. I also want to point out that when they kind of do this stuff, they're using equations that we discussed. So, for instance, this one is and this one, which is kind of the equations for the statistical moments. They're using the expectations and the one that we have been discussing before. And I also want to point out that sometimes people say, "Oh, we have zero padding," and we also talked about that. If you have an FFT in MATLAB and it is not in a power of 2, it will zero pad it in order to get it to a power of 2. Now, the zero padding is the same thing as adding or as applying a window, because the zero is basically is 0, and then the window is kind of 1 at the point where it's not 0. So you have again the product of two functions. Then the other thing, and I'm not going to talk about that at all further, is the multi-taper method that is outlined in the textbook, but that's kind of a lecture in itself. The only thing I want to say about the multi-taper method is that it looks like the standard Fourier transform, but it's using tapers in a smart way. And the idea is that the spectral leakage, which is caused by the fact that the tapers spread out the energy a little bit, and noise, because if you add precision to your spectrum, you also add noise. These issues are kind of addressed in the multi-taper method. For this particular example, it's not that important because you have a lot of repetitions in the individual measurements that are leading to the average. So for that reason, I'm not pointing that out too much here. So let's kind of go back to this time frequency analysis. And again, that's something we may actually talk about Wednesday as well. But we already said that the tile that is associated with the spectral analysis is related to the time that you pick, and the time and the frequency of the tile are kind of related to each other. So if you have, for instance, and this is a wavelet at a large scale, if you take a longer time, then basically 1 over longer time is going to make a small frequency resolution. If on the other hand you take a smaller time, then you have a smaller time base, but you have much worse resolution in the frequency domain. So that means that if there is some sort of a local high frequency, and you're using only this scale, you're gonna kind of see something there, but you're not going to be able to say where it occurred. And of course, if you have non-stationarities in your signal, as it is the case here in this evoked potential, then yeah, that can be an annoying aspect. I think this is kind of a nice central figure where things are nicely compared. So they look at a single trial spectrum. They look at an average spectrum, so that's the result of the average, and then they look at the difference between this spectrum and the beginning, the part that is taking place before that the stimulus occurs, because here is where the stimulus is, here is pre-stimulus, and this is post-stimulus. And so if you divide this spectrum by this part, you will get the change in power. So what they did is they used they used tapers, and they have a short taper, and you can see what a short taper does for a high frequency and a low frequency. Just an example, 2 frequencies. They could have picked more frequencies. They could have had a longer taper, again, this high frequency and this low frequency. You can have multiple tapers. In this case, that's the multi-taper analysis. I'm not going to say much about it anymore. And then you have the wavelet, and I'm going to say something about that and maybe a little more Wednesday. So what we have here is, if you have a short taper, we know that the taper in time domain is short, and the associated frequency analysis or frequency resolution is also decent. However, if you take a longer taper, like here, you have longer distances between the windows, but of course the time is longer. That means that the distance in the frequency axis is shorter, and so you have better frequency resolution. Since they are using similar distances here, that's the same, although one of the disadvantages of the multi-taper approach is that you will lose a little bit of frequency resolution, and you can see that here. The wavelet approach is nice because it actually uses tapers adaptively. For the lower frequencies, it uses long tapers, and for the higher frequencies, it uses less tapers. So it means that higher frequencies are more precisely determined in the time domain. Of course, the disadvantage is they're not as precisely located in the frequency domain. And here you see the color-coded versions of this whole thing, and you can see the advantages, disadvantages. You can see, for instance, in the wavelet transform, you can actually see, certainly in the average, where the low frequencies occur and where the higher frequencies occur. That's, for instance, in this difference plot, very clear. On the other hand, this one does a pretty decent job, the longer taper. One of the things that is noticeable, and I think that's important to point out here, is that they actually have this 120 Hertz artifact sitting here, and they have the gamma rhythm that is their response nicely present here in these plots. The problem is the gamma rhythm is 45 Hertz, and the artifact due to the hum is 60 Hertz. That's a little bit too close for comfort, isn't it? So that would be one major critique, not so much on these people that did the analysis, but definitely on the people that did the recording. And this kind of goes back to something I mentioned when we talked about signal averaging. So why is there a 120 Hertz artifact in here? And would there also be 60 Hertz? Well, we already saw in the power plots that indeed there is. Why is it there? Well, because there is a 120 Hertz harmonic in the input, and so that means that the shielding is probably not as good as it should be. But I think the most important thing is they use a stimulus interval of 600 milliseconds. That's probably not that smart, because it may not help you getting rid of it. Is there also a 60 Hertz artifact? Because if there is a harmonic, is the base frequency also there? And the answer is yes, it can be seen in the spectra. I already pointed it out. And the reason is the same as above. You need good shielding. And in the color pictures, the 60 Hertz is somewhat masked by it's at 50 Hertz, but it should be 45 Hertz biological response. And I already mentioned that I think it's a little bit too close for comfort. So what could you do about it? Well, shielding would be the first thing, but of course, once you have it recorded, shielding is not possible. But you could, or once you have a rig that is difficult to work with, I mean, it's difficult. You could have taken a different interstimulus interval, of course, because look what happens if you use an interstimulus interval of 600 milliseconds, and this is just a simulation of 120 Hertz. if you start averaging that at a rate of 600 milliseconds, your average will have a lot of this 120 hertz. And you can copy and paste this in your MATLAB and run this, and you will see that that is what happens. On the other hand, if you change it a little bit, let's say you do 650 milliseconds, so that means that double the number of samples. Look what happens. Look how small it is now. So basically, by changing the interstimulus interval a little bit, you get rid of your annoying 120 hertz. And I'm not going to show it to you, but you can also play with this value to optimize the interval to get rid of the 60 hertz hump as well. And this is the figure that we use to talk about this. Wavelet transforms. We kind of looked already at an example. I just want to point out again that there are 2 chapters in the textbook that deal with this. Good. Well, we talked about 120 hertz. Let's now talk about the matching pursuit algorithm, because that's basically the thing they wanna sell to us as the best thing, isn't it? So they are going to, and we are going to look at that figure. We're going to look at this by having different tiles. They kind of define a bunch of tiles. A priori, they call that a dictionary of atoms, and then they basically grab the atoms sequentially, the atoms that fit the best with the signal. We're going to talk about the detail a little bit more in a bit as well. And then they keep kind of going at this, and then based on that, they are going to create a time frequency spectrum. And here is that figure. So here are the tiles that they basically have. That's part of a couple of tiles. This is not all of them. They have more tiles in their dictionary, but they show you a couple of tiles. And they show you the signal here in green. And they then show you how the signals, these atoms, basically fit in these atoms, fit with the data. And then based on that, then for instance, I don't know why they put it in this way, but let's kind of look at this one. Here you can see that at this octave, this atom, this 5th atom, that they can fit this signal with this atom like as follows. And if you basically put that into a color bar, you will see that this looks like this thing. And this is indicated, by the way, by this black rectangle. That's not that clear in the original figure, but you can probably see that there is a black rectangle around this. And for instance, there is another one that does the gamma rhythm quite well. In this case, this one is not the same as that one, but you can see that the gamma rhythm is also nicely done. So now you can basically start to collect all the data from all these different atoms, and then you can create a time frequency spectrum based on the fit with the different atoms, and that is what is shown here. So now you can see indeed that again, this is a single trial spectrum, an average spectrum, which is way smoother, of course, and the change between the pre-stimulus and the average spectrum. And here you can see a number of things. Indeed, the nice response is clearly there. This 120 hertz line, annoying, it's also still there. But you can clearly see that after the stimulus, you get this nice read the 45 hertz frequency band. But by the way, I always say, well, it's always a good idea to also look at your data. And if you just look at the time domain data, you can actually already, if you look at figure 1, for instance, you can already see in the time domain that there is a 45 hertz rhythm there. So you don't need to jump through all these hoops to kindly come to this conclusion. It's a nice way of displaying it. I won't debate that, but it's certainly something you can see by eye in the time domain average. So there are some limitations, and I think they are kind of self-explanatory. Then they promise that they look at the Hilbert-Huang transform, but they don't show any data of that. In the textbook, I talk about the Hilbert transform, and the Hilbert-Huang transform is basically a combination between decomposing the signal in empirical components and then applying the Hilbert transform to these components. If you are interested in that, you could certainly look at the Hilbert-Huang transform for your LFP data. And this is what I just said, is that if you look at figure 1a, you can actually show that 45 hertz rhythm. I keep saying 50 hertz, but it's 45 hertz. So now a little bit of the math. So we have here the multi-taper method, which I didn't talk much about, but it's basically the same thing as using a taper. But you know what's better than one taper? That's multiple tapers. You have seen already that it loses a little bit of frequency resolution, but on the other hand, you get less leakage and you get less noise in your spectrum. The wavelet transform we're going to talk about later as well, but it's based on the correlation between a signal and the wavelet. And the wavelet is basically either wider or shorter, and that is the scale. And of course, the wavelet can also move over the signal, and that is the position u here. And that's what a wavelet is doing. But since this is a paper about matching pursuit, let's kind of talk about that. And the idea is that you have a dictionary of signals, and they call that atoms, and you are going to decompose your signal by picking the atoms one after another as they fit best. And that thing is called a greedy algorithm. It is greedy because it takes the best fit first. Of course, if you do not have issues with local maxima and other complications, that works relatively well. If you do have multiple local maxima, etc., then this may not work that well, of course. In this case, they are going to then say, well, we grab the atom, we then kind of see how well it fits. We take the best fit, but how well it fits, and then there will be a residue of the part that is not controlled by the fit, and then I'm going to take the next atom that fits the residue, and then again I will have some residue, and then I'll take the next one, etc., etc. So it looks a little bit like this, and I thought this was a nice one for Wikipedia explaining a greedy algorithm. If you are working in a supermarket and you have to give somebody 36 cents back, then basically how do you do that? And you have coins of 20, 10, 5, and 1. Well, if you are applying a greedy algorithm, you pick the 20 first, then you get 16 left. Now you cannot use 20 anymore, but you can use 10 as next. That's the next big thing. And so now you have 6 left. Now you cannot use 10 anymore, but you can use 5. And now you have 1 left. And then finally you use 1, and then you have 0 left. So now you basically have, in a greedy fashion, you have determined how to sequentially return your change. So it's a nice site on Wikipedia that also gives you some other examples. But this, I think, drives the message home how a greedy algorithm is working. And that's in a way what they do. They have a signal, that's your 36 cents. and they have coins, your atoms, these are your coins, and they see just how can we fit the coins to the signal. There is also a nice example in MATLAB how that works, as on this side, with some examples that I would recommend. Here, for instance, they say, well, let's say that we have a signal, that this vector is our signal, and let's assume that this is our dictionary. And then they plot that this is your signal, and this is the atoms in your dictionary. By the way, they made a little mistake here, because that arrow should go up to 1, and this also should go up to 1. So, but that's really not that important. It's just, I mentioned it here. So here you say in MATLAB, my dictionary is these points, these guys. My signal X is this thing. And now I am going to see how this is going to fit. So what you then do is you kind of create a scalar product of your signal with the dictionary. And within that scalar products, you pick the largest one. So you're greedy, you pick the largest one. So in this case, that will be this vector, this one. And then basically you then determine how much is explained by that vector, and then you subtract that from X. And I'll come to a detail a little bit later as well. And that is your residual. And then basically you kind of start to repeat the whole thing. You now apply the whole thing again to the residual, albeit in this example they already take away dictionary 3 because that already was used for fitting. The problem is, and I will explain that later also, is that this is not like, for instance, in the Fourier transform or in other transforms, that all the components are perpendicular or independent of each other. So that's kind of a little bit of a problem potentially. I basically show you this in a simple diagram. So let's say that we have our signal X, or the first or the second or the third residual, that doesn't matter, but this is the target that we want to do. We then kind of find the best atom. Let's say that this is the best atom that we find. We then basically take the projection of the signal on that atom, that is the component of the atom that explains this signal, and then you subtract the difference. So and then you find the residue. So this is basically the signal. This is the explanation of this particular atom, and this is the residue, the part that's not explained by that atom. And you can see that basically the residue is indeed orthogonal to this projection. But if you now start to kind of repeat this thing with another best atom, then of course that will not be orthogonal necessarily to the original one that is here. So that means that the different projections and the different components may not be independent. There is a version of that, and you can find that on that same website, and that's called the orthogonal matching pursuit. And the idea there is that you're kind of using what is called the Gram-Schmidt method that creates, by definition, by design, creates orthonormal sets of atoms. So if you ever want to think about using matching pursuit, I would strongly suggest that you look at this alternative, because in a way that is nicer, because now your different components are truly independent. So now we have the signal and we have a bunch of atoms. Now we want to kind of create a spectrogram of that, isn't it? And that's explained on that last page. It says, well, basically we use the Wigner-Veal distribution, WVD, so it's kind of the abbreviation of the initials of my name. But it is kind of related to the Wiener-Kindchen approach, because recall that this was the Wiener-Kindchen. If you now remove that integral and you kind of change the time difference between t and t plus tau and t minus tau half, t plus tau half, then you kind of get an instantaneous power type of expression. And now what you can do is you can take your library of atoms that you have used to fit to your signal, and you can make a time frequency distribution for each of the atoms. You also have the weight, because these we determined for each the projection of your signal on that atom. So you have the weight of that projection. And then you can, in principle, kind of use that to your Wiener-Ville distribution, and then you get an expression like this, where you see that the energy distribution in tau and frequency is just the sum of the power of the atoms in time and frequency expressed. And that is, in principle, what they showed in that figure, where they apply the matching pursuit. And here I think I stop. We can also stop the recording, and we'll hang still on in case you have questions, etc.